Welcome to our first virtual presentation, Unlocking Concurrency and Performance in Python with ASGI and Async IO. Our speakers, as far as I understand, as I'm looking over to the side, they're not hiding behind the curtain. You can pay no attention to the man behind the curtain. There is no man behind the curtain. There's a laptop. But gentlemen, you're coming in from India, is that correct?
Yes.
Okay, well, thank you for being up very late so that we can all sleep off our Saturday night and enjoy a Sunday morning. We have Alan Y. and Aswin Kishore. I also understand we'll have a remote moderator. Anders is going to be moderating the session here. So I will hand over to our presenters and to Anders, and I'll be back when the presentation is over. So enjoy.
Thank you. Hello everyone, we are thrilled to be here at PyCascades 2025 to talk about the topic Unlocking Concurrency and Performance in Python with ASGI and Async IO. I'm Alan Y, a backend engineer at Stored by UST, working on scalable systems and microservices. I'm also an open source contributor and love sharing insights on Python's evolving ecosystem.
And I'm Aswin. I'm working as a backend product engineer at Stored by UST. We are building a travel platform. I'm specialized in GraphQL Python ecosystem. I'm also an active contributor to many of the GraphQL Python repositories. Over to you, Alan.
Yeah. So today we'll be sharing outlines on introduction to Async IO breakdown, performance, ASGI versus WSGI server, and some of the best practices to be followed while using Async and ASGI. So before we dive into Async and ASGI, we need to discuss two concepts that have been often confused. So parallelism and concurrency. So parallelism is basically ability to execute multiple processes at the same time without these processes or tasks being interleaved. So what is a process? Process is basically a set of instructions. Process is basically a program under execution, and program basically consists of a set of instructions. So it's the CPU which does the execution of these programs. So for each CPU, we have cores. Let's say we have n number of cores. Each core can handle a single process at a particular time. So basically, if we have one core, only one process can be handled at the time. So ability to handle or execute multiple programs at the same time, process at the same time is called parallelism. So now moving on to concurrency. Concurrency means making progress on one or more tasks seemingly at the same time. Let's say we have a single CPU core and two processes or two tasks that needs to be executed. Let's say task one gets starts execution under the core, and let's say task one has to make a network request or an IO code. So it has to wait. So during its waiting period, it transfers its ownership to the underlying file descriptors of the OS. So during that time, the task one is sitting idle. So the core is free. So what the core does is it preempts the task one and allows execution of task two. So here we can see that task one and task two are not parallelly executed, but they are making some progress by interleaving execution. So this is known as concurrency. So now moving on to multi-threading. So what is the thread? Thread is the smallest unit of execution of a program. Let's say there's a particular single process which is running. We can divide the whole process into n number of parts such that each part, when combined, can do what that single process can achieve. So these n parts can be executed by spinning up n number of threads such that each thread execute each part of the program. So here we are kind of executing all the parts simultaneously using multi-threading. So in Python, multi-threading doesn't work the same way as we expect because we have GIL. So what is GIL? GIL is a global interpreter law. It's one of the most controversial features in Python, which restricts parallelism in Python. Let's say, so interpreter is the it's the one that converts a high-level code into Python code to a machine code. So let's say we have n number of n threads executing a single process, and let's say a first thread is execute its bytecode onto our interpreter. So when a thread enters the interpreter, it has to acquire a log which is present inside the interpreter. So while execution of bytecode, it has to acquire that log of the interpreter. So while that is being executed, and if a second thread tries to come and execute its bytecode, it won't be able, because since the first thread has already acquired the first log, it won't allow parallel execution of second thread. So multi-threading doesn't support parallelism in Python. So we needed, and another disadvantage of using multi-threading is that so when we create multiple threads for a single process, even though like they might have different stacks and registers for each thread, but each thread share the same code section and data section of that particular process. So there might be race conditions because multiple threads may try to access the same variable or data present in that process. So we needed something that is a single threaded, but at the same time provide concurrency. Ta-da! We have Async.io here. So Async.io does not block. Instead, it suspends a task while waiting and runs another. Under the hood, we have many like event loops inside Async.io. So which will be deeply discussed by Aswin. So handing over to you, Aswin.
Thanks, Alan. Let's deep dive into Async. So here I have two syntaxes. This is the latest Python that we have available right now. We have the proper async await syntax, that is async def functioning, and the await syntax. But before this was introduced in Python 3.4 and below, we had to use this weird syntax. Basically, you have a synchronous function, and in order to make it async, you had to apply a decorator. That's async.io.coroutine. And then instead of the await syntax, you had to use yield from that particular function. And then instead of this async.io.run, you pass the coroutine here. Instead of that, you had to do this async.io.get the event loop, and then call the run until complete function to run that coroutine. So this is the key syntax difference that occurred over that period. Now let's try to understand what's an event loop. Okay, so this is a critical architecture. So we have a main thread in the Python. It submits tasks to a queue. Okay, so there's actually a loop here that is going to take a task from this queue. It's going to execute it, and when it encounters a blocking operation, what it's going to do is it's going to pass it to the OS to handle it. And then it's going to check if the task is completed. Let's basically ask the OS if it's completed. If not, if yes, it's going to unpass the task and then continue the task itself. Otherwise, suppose it is not completed, then what it's going to do is it's going to take another task from the queue and then process it. And this repeats until all the tasks are completed. This is actually the simple architecture of event loop. Now let's also demystify something. So this is actually the code I stole from Async.io, the library itself. So here you could see that there's a small code called self.run forever. This function we are familiar. We just wrote it in the before slides, right? So here we have self.run forever, and inside this you could see that there's indeed a while loop here. That's what I was talking about. It is actually a simple while loop. So now let's discuss the types of loop. So there are two types of loop. One is a selective event loop, and another is called the proactive event loop. So in the selective event loop, we have functions, the OS commands that it uses is select, poll, epoll, and kq for Mac OS. These are for Linux. Let me try to make you understand it. So basically in the select command, you pass a list of file descriptors. Like let's say I'm the process. I am passing it a set of file descriptors that I wish to read from, set of file descriptors that I wish to write from, and a set of file descriptors that I wish to means expecting some exceptions from. So this is going after I pass it to the OS is going to tell me that the out of the file descriptors I passed, some of these are ready for reading, some of these are ready for writing, and some of these are ready for exception handling. So this is the call that is being done to this OS. So here you could see that the process needs to poll the OS periodically to get this information. So that's why we need to check for readiness here. And one key thing to note is that this does not work on Windows properly. By properly, I mean that there's a small limit. Like in the select function, it only supports like 512 file descriptors in Windows. So the reason actually is that Windows has a thing called IO completion ports, that is IOCP, and this proactive event loop, this is actually primarily meant for Windows. So the key difference here is that instead of the process polling the OS periodically, Here the OS itself will tell the process that this task is completed. So that's the main key difference between the selector and the proactive event loop. And this is only available for in Windows. Yeah. Okay, now let's discuss about Async IO hierarchy. So here we have an await class. This is a base class. It is inherited by coroutine, future, and future has a child known as task. So let's discuss about awaitable. So it's actually a class that has an abstract method known as underscore underscore await. Okay, this underscore underscore await method is what enables us to write that await syntax in the code. Okay, let's look at an example. So here I have a simple awaitable class inherited from the awaitable subclass. The parent. So here I'm defining that abstract method await. Here what I'm going to do is I'm going to call the asyncio.sleep method. And here you could see that I'm calling the underscore underscore await method of this one. If you notice, this is actually a coroutine. What is the coroutine subclass of? It's actually a subclass of awaitable. That's why I was able to access this. So here I am yielding from this this coroutine here and simply passing the value that is passed in the constructor. So here you could see that I am creating an object of symbol awaitable and awaiting on that object itself. And this is a simple example of awaitable. Now let's look at futures. So if you have done JavaScript before, there's something called as promises there. So future is something similar to that conceptually. So here future is something that we expect, like we create it right now, but we expect that sometime in the future someone will set a value to it. That's actually the principle behind future. It's the result of an asynchronous operation. Let's look at an example. So here I have a future instance, my future. Here it has a couple of methods like done, result, set exception. So let's look at the example further. So let's assume that someone else is setting this result in the future I declared here. So let's assume that. So here you could pass any result to it. And then when I'm checking the done, initially it was done as false because this future has not been set by anyone. But now if I check it, it's actually true. And how to access the result? You have the method called result to access the value passed by someone else, right? Okay, and suppose you want to actually, maybe you did some computation and some exception occur. You have to pass that to the caller, right? So you can use the set exception method and pass the error there. And when you are accessing the result, you are going to get that error thrown out. So you need to do a try except block to catch it. Suppose you don't want to catch it. In that case, you could simply do my future.exception. It's going to return you that exception without throwing it out explicitly. Now let's look at coroutines. It's basically anything that begins with async def syntax. It's a function that is capable of pausing its execution. What I mean by that is you write await lines inside a async function, right? Those are the lines that tell the Python interpreter that this function can be stopped at that point of time. When it is paused at that point of time, a Python interpreter will process other coroutines or other functions concurrently, right? This is what enables us to do the asynchronous execution in Python. So these are the two keywords. Async keyword creates the coroutine, and the await keyword passes that coroutine which is under which it's declared. So let's look at an example. It's a simple example. I have a simple square function. It's actually not an async function. There's nothing blocking here, but just for an example purpose. So here we have returning the square of a number. You could see that I call the function square of 10. If this was a synchronous function, you would get the result as 100 here. But this is a coroutine. You could notice that if I'm printing this, I'm getting the coroutine object here. So this the function has not been called yet. And there's also a warning thrown by the Python interpreter. If you wish to, it was not awaited. If you wish to get this warning, you can set Python trace malloc as 1 in the environment variable to get this error. It's a useful thing when you are debugging async things. Okay, so I'm going to write the proper syntax now. So I have declared async def main here and awaiting the square of 10, the function here. So I get the result 100 as expected. And I'm passing this coroutine in the async io.run thing. Now let's talk about task. Task is actually a subclass of future. It actually represents a coroutine that is currently being executed by the event loop. I have mentioned about that queue, right, in the event loop architecture. So that event loop, the queue actually contains a list of objects that is created from this task class. Okay, this is how you schedule coroutines in Python. Let's also look at an example to understand it further. So here I have a simple coroutine function. I'm simply waiting it for 5 seconds and returning success. And there's a small try except block here. I will come to that in a moment. So in order to create a task, you call asyncio.create task and pass a coroutine to this. And you simply you pass to it. Okay. So you could see that the coroutine has started. The first line has started executing. I'm simply doing a sleep of 2 seconds. And now let's check if the task was actually completed. False. Why? It's actually going to take 5 seconds for here. 5 seconds to complete this line. But I have only waited for like 2 seconds. Okay. But now I want to do something interesting. I want to cancel this task. Let's just assume I created a task. Later I don't wish to want it. So I can easily do that too. I can cancel the task. Now, if I'm actually checking if the task was actually cancelled, Python tells me no, it hasn't been cancelled. But because why? This 5 seconds is actually still being processed. Only after this is completed, the Python is going to execute the rest of the code. Okay, so let's actually await the task so that the rest of the code is also executed. Now you could see that I got the result as failed. That is here. I wrote the try except thing here because you could actually write it here or you could write it here also. Both are fine. So the async IO library is going to throw this error, and you need to catch it if this task can ever be cancelled, right? So if in the result also you get the failed, and when it's done, it's actually returning as true as well. Yeah. And also, suppose you want to schedule tasks concurrently, like say if I want to schedule 5 tasks at the same time, you can do that. You can use the async IO.task group here. So here I have a simple coroutine here. It's a function that's going to sleep for like maybe a given amount of delay. And in case the task name is 3, it's going to throw an error. Okay, keep that in mind. So here I have the syntax to create a task group. So async with async IO.task group. This is actually the syntax of async IO. Async context managers. If you're familiar with file opening, you use with open, right, for opening files. Instead of that, in the async way, you have to do async IO async with syntax. Okay, so in order to pass the task, I'm simply calling tg.create task 1, task 2, task 3, task 4. Okay, it's waiting for 2 seconds, 1 second, and so on. Okay, now let's look at the output also. The moment I do this, when I come to this line, task 1 is created, task 2 is created, task 3 and 4, so on. So till 4, all the tasks are created concurrently, like at the same time, right? And then you could see that the least amount of time is for task 2. That is, it's only going to sleep for 1 second. So you could see that task 4 was completed, then 2 seconds, that is task 1 is completed. Now, the interesting thing is, task 3 is going to take 4 seconds, right? It's going to be completed before task 5. But what's the problem? It's going to raise an error. So you could see that the error was indeed raised, and I got it using the exception group here, and that's what I have printed here. But you could see that task 1 was never completed. You can see there's no completed here. Why? Because task group works in a way that it's going to cancel all the remaining remaining tasks that are still running if one of the tasks got an error or something and an exception. That's the principle behind task group. So you could see I'm also printing the result just to clarify that. Task 1 has a result, great. Task 2 actually got the cancelled error. There's no result here. It was actually cancelled due to the task 3's value error. See, that's the interesting concept. Suppose you don't want this to happen in your code. In that case, you could use the async IO.gather. It's similar to task group, except it has an extra parameter called return exceptions equal to true. If you enable this, it's going to process all the tasks, and even if one of them fails, it's not going to forcefully cancel other tasks. So you could see that this is the syntax async IO.gather. You pass the task one by one, and then pass the return exception equal to true here. So you can see that task 1 started, task 2 started, and task 1, 2, 4, all these completed, all of these were completed, except for, I think, task 3, right? This is the one that's going to raise the error. And you could see in this array that all of them has a result, except for the third task. It's actually the exception that was raised by this task. Okay. Now, let's also talk about the impact of async IO in the everyday task in Python, right? So on the left-hand side, I have a simple synchronous code. On the right-hand side, I have an asynchronous code. The concept is I am going to sleep for a limited amount of time. Let's just assume this is some complicated, maybe some blocking IO. Okay. So in the code here, it's going to sleep for the delay you passed here. And here I'm doing it in the asynchronous way using the async IO.sleep. Okay. And I'm going to create 5 tasks on both of these code, and I'm going to keep the delay same, like let's say 2 seconds. And I'm going to do a benchmark test using the perf counter. Okay. So now you could see that task 0 started, task 0 completed, task 1 started, task 1 completed. It's one after the other. Like only after task 0 is completed, task 1 is actually started. But let's look on the right hand side. All the tasks were started at the same time, and all the tasks were also completed. But if you notice the time taken, it's actually 5 multiplied by 2. That is only, since it's synchronous, it's going to take 10 seconds. But on the right hand side, it only took us 2 seconds to do this. So we could see that how much time we could save using asynchronous code, right? Okay, now over to Alan to give you an insight on how async works in servers. Over to you, Alan.
So WSGI. So WSGI stands for Web Server Gateway Interface. So basically, it's a standard interface between web servers and Python web applications. It allows web applications to communicate with web servers in a structured way. Basically, WSGI is just a protocol. That's a set of rules that defines how a web server should talk to a Python web application. So between WSGI, between a web server and a web application, we have a WSGI protocol. That's a set of rules, and we have a WSGI server too. So I think everyone will be familiar with Unicorn. Unicorn is used to run Django web apps, Django Flask. So another feature of WSGI is synchronous. Synchronous, so it's blocking. So when we make a single request, and it has a waiting IO operation, and when a subsequent request comes, so it has to wait until this first request is completed. And it also follows the traditional request response cycle. So this was an overview of WSGI. So WSGI has certain limitations. So since it's synchronous, as mentioned earlier, it's blocking. So subsequent requests can only be processed until the first request is totally processed and completed. And it is it's not scalable. Scalable in the sense, since it follows the traditional request response cycle, it is not suitable for WebSockets or real-time communications, and it's resource heavy. Resource heavy in the sense, since it cannot process multiple requests parallelly, what it does is it spins up we can spin up n number of workers where n is equal to 2 times number of cores plus 1. So each time we spin up a worker, we need to provide the exact configuration of the web app we are running. So it's totally resource intensive, resource hungry. So these are some of the limitations of WSGI. So in order to improve the performance of our web applications, we can have an async version of WSGI. So that is ASGI. So basically, ASGI is WSGI plus support for async protocol. So it supports both synchronous and asynchronous operations, and it is highly scalable because it's suitable for WebSockets, polling, etc. So between our web server and a web application, we have the ASGI server. So example for ASGI server is Unicon. So Unicon is responsible for running a FastAPI app, web app. So some of the advantages of ASGI or WSGI, let's discuss that. So since it's asynchronous, it can handle multiple requests concurrently without waiting for one request to complete. It is highly scalable because it can support WebSockets and real-time communications. And since it's concurrent and it uses event loop, it is non-blocking. So what it does is we don't have to spin up n number of workers to handle multiple requests. Event loop monitors subsequent requests, and if there's any waiting for a particular request, it just moves it out of it suspends that particular request, and the subsequent request can be processed at the same time. So that's how ASGI increases performance. So now let's discuss some of the best practices while using async in Python. First is a package called AIO HTTP. So traditionally, we'll be for making any web request or API request in Python, we'll be using the request package. But it has a if you are making higher number of requests, it's not preferred because the request package is blocking. So making large number of requests simultaneously would slow down the process or decrease the performance. So instead of that, we could use AI HTTP package. It's non-blocking and asynchronous version of this. So let's say you make n number of requests. Since it is non-blocking, it can process all those requests parallelly, and the processing time of each request and the performance can be increased to a great extent. So this is a basic example of code snippet for using AIO HTTP. The syntax is almost similar. The only difference is we have an async context manager. Inside that, we'll be making the request. Similar to AIO HTTP, we have something called AIO files package for reading file operations. The traditional open method for reading or writing into files, it's blocking. So reading from a large number of files or writing into a large number of files could be a time consuming process. So instead of that, we could use this package AIO files. So it's basically non-blocking. It's same. So it could process large number of file operations at a very high speed. So its syntax are also similar. We just have to use async context manager there. So inside that we will be defining our write operation or read operations. So we'll end this talk with a quote by one of our AI ChatGPT. So in async programming, patience is the key, but only for the task, not for you. So these are some of the references which we had. So thank you for listening. If you like, these are our social handles. Feel free to connect with us anytime. If you have any queries, you can reach out to us directly. So thank you once again. We are ending up. Thank you.
Over to you, Josh.